the next chapter is going to be the power series solution for linear differential equations. From previous chapter, what you have learned is how to solve for the solution of linear differential equation which has constant coefficients. And many times that you will see the equation which is the coefficient is a variable. So in that case, you cannot use the previous technique to find the solution. For the power series, one method that you can use whenever you have the variable coefficients for your linear differential equation. For example, for the Bessel equation, the general form of the Bessel equation is look like this, and P is just a constant. P is just any number. If you take a look at this, you would see that if you assume that P is equal to 0, so you would have the x squared y as the last term of your Bessel equation. The thing is that this equation is having the variable coefficient. So from the previous technique, you cannot use to find the solution for this differential equation. And you also cannot use the Cauchy-Euler equation because it is not in the form of Cauchy-Euler. From the last part of that equation, it obviously shows that it's not Cauchy-Euler. So in that case, you have no way out to find the solution of this differential equation. Another example is the Legendre equation. If you can see that, of course, this is not Cauchy-Euler. It's still in the form that having the variable coefficient for your differential equation. So if you have this type of differential equation, the way that you can find the solution is by using the power series. Okay? So for power series, what you have to do is just assume the answer of the differential equation in the form of the power series. Y is equal to summation of an times x minus x0 to the power n, where n is from 0 to infinity. That is the assumption that we put there. So in that case, we should have known the power series of the general function. For example, 1 over 1 minus x. If you want to write down this term in the terms of power series, it says that 1 over 1 minus x is equal to summation of x to the power n, where n is that from 0 to infinity. Just the same meaning. Or if you want to find the exponential, you know that the exponential is equal to summation of x to the power n divided by n factorial. For cos and sine, here is the power series which is expressed in terms of cos and sine. And also cos hyperbolic and sine hyperbolic, and ln 1 plus x. This is just the function that you should know. So now, like when you solve for differential equation, if the term that the final solution that you got is in the term of the power series, for example, if it is equal to summation of x to the power n divided by n factorial, then you would know that it's equal to exponential of x. So now it might come up to your question. You might have the question in your mind that in that case, if you have the constant coefficient, can you use this technique to find the solution of differential equation? I would say yes, of course. But this one is more complicated in such a way that not everyone knows that this type of function has the power series in what form. So that's why if the differential equation that you have can be able to solve for the solution by the previous method, we pick the previous method. method that we learned. Okay. And before I give you the example of the way to finding the solution by using the power series, let me tell you this first. It's kind of the property of the summation. If you have fx is the function of f by expressed by this power series, and g is expressed by this power series. I said that this problem statement asking us to find the summation of fx and gx. The way that you do, you just put both two functions and do summation of them. And then, since you have the starting point of your summation from n equal to 0 to infinity, then these both terms have the same function. You can do summation by put the constant of both of them and plus them together. Why we can do that? I mean, if you distribute this term, you would say that you would get a0 plus a1x plus a2x squared until infinity. Okay, and for the term g, you would get b0 plus bnx plus b2x squared until x to the infinity, x to the power infinity. The way that you plus them together is just that you put the terms which has the same function and plus them together. The first term a0 and b0, actually they have like x to the power 0, but you didn't write down because it's equal to 1. So these two terms, you can plus them together. You cannot put a0 plus b1x, right? Okay. So the first term you would get a0 plus b0. And the second term you would get a1x plus b1x. So they have x which is the same, so you take x out, so you would get a1 plus b1. And you do the same for the next term. So you would get a2 plus b2 times x squared, and the next term will be a3 plus 3, and the whole thing times x to the power 3, and so on. So that means this function, you can write it down in the term of summation. So you would get n equal to 0 to infinity of a n plus bn times x to the power n. Okay, so this one is just want to give you some idea of the summation of the power series. Okay, so if you cannot do this one right away, the things that you can do is just that distribute each term of this and then write it down like this, and then try to find the form, the final form by yourself. Okay, now let's see what we are doing for finding the solution of differential equation by using the power series. As I said that, for the power series, what you can do is just that assume y to be this form. Summation of n equal to 0 to infinity of an times x minus x0 to the power n. X0 could be any number. Could be any number. Let me show you to find the solution. I haven't taught you about the technique to find the solution by power series, but I want you to know the method slowly, and then I'll show you. I'll teach you step by step again. But this one, I just want to tell you that no matter what you use this technique or the previous technique, you would end up with the same solution. Okay. Find the solution of this differential equation. This is the second order differential equation which has the constant coefficients, and it is a homogeneous differential equation. So the answer of this differential equation would be y3 only. Right? So to find this to find the solution of this differential equation, you get to write down the characteristic equation. From this, you would get m squared minus 1 equal to 0. So you find two values of m, which is m equal to minus 1 and 1. So which is in the first case of our differential equation, right? The root of n is the real, unrepeated real number. So the solution would be c1 times exponential of minus x plus c2 times exponential of x. Right? This is whatever you learned from the previous chapter. Now, I'm going to use the power series to find the solution of this differential equation. Like I said, for power solution, the power series, you have to assume that y is equal to an times x minus x0 to the power n, where n is equal to 0 to infinity. I said that in that case, I'm going to find a solution where x0 is equal to 0. So now my yn is equal to an x to the power n, where n is starting from 0 to infinity. Because this y is the solution of this differential equation. If I want to find y, I have to put y back into my differential equation. My differential equation saying that you have to do derivative of y 2 times. So then I do the first time. The first derivative of y